Great. Okay, so like Shane said, I'm going to talk a little bit about some work that I've been doing trying to use large ensembles to constrain future estimates of temperature variability. But a lot of this talk is actually going to be around how we evaluate which models are good, and then we try and use those to project the future. But before before I go into the details, I'm going to just quickly introduce what I mean by large ensembles, because they have the word large ensemble has sort of different meanings across different communities. And what I'm really going to talk about here are what we're calling SMILES, which are single model initial condition large ensembles. So these are basically CMIP class models that have perturbed initial conditions and are run with exactly the same forcing, generally between 20 and 100 times. And so what you get from that is you get a range of evolutions of the climate model that are really only different because of internal climate variability. And you can see that on the plot here. You can see a bunch of different SMILES for precipitation anomalies over, this is the Colorado River Basin, and you can see that each kind of solid line is the mean across the ensemble, which gives us an estimate of the forced response to climate change or increasing greenhouse gases. And the spread around it are those ensemble members, which give us an idea of the spread due to internal climate variability. So really what we think these SMILES are really useful for is being able to actually quantify the forced response by averaging out the internal variability, but by also being able to look at the magnitude of the internal variability itself, both in present day and in potential future climates. And before I talk about actual research, I just want to spruik this archive that I've played a bit of a role in putting together, which is a multi-model large ensemble archive version 2, which is a giant mouthful. But it's basically all of the SMILES that are currently available that have been regridded to a common grid for 11 different variables. So we've got 16 models and 11 variables all on the same grid that are going to be available on the NCAR website really soon, but also I've actually just finished porting them over to the NCI. So they're available for Australian use at the moment. And we've run NCAR's climate variability and diagnostics package on all these large ensembles, which is really cool because you can look at the different models and see how they perform compared to other models for a giant variety of metrics. And you can see that on the table to the right, where you've got a root mean squared error difference for a bunch of different metrics for each model, and a mean score on the right. And the cool thing that we did with this package is that you can run it for each ensemble member. So you can see if your evaluation would be different if you had a different member. So if the internal variability is affecting how your model evaluates against observations. And you can really see that on the next slide here, which shows ensometrics, because I'm interested in ensometrics. But you can see here a pattern correlation for different metrics for each ensemble member in the little solid lines. And so you can see for some metrics, you can get quite a large range of pattern correlations with observations just because of internal climate variability. And so all of these plots are going to go up on a web page based out of NCAR. So you can just kind of click on them and see how the models evaluate. And ACCESS ESMWG is in there with the large ensemble. And so that's kind of cool. It might be something interesting for this community to look at. Okay. So I just want to spruik that before I talk about science. So moving on to the science, what we really wanted to do in the project I'm going to briefly introduce here is to constrain future projections of temperature variability by looking at which of the large ensembles or the SMILES agree well with observations, selecting the ones that actually agree well, and seeing if the future projections are more consistent and less all over the place if we do that. And this was really we wanted to do this because of this figure here, which comes out of the most recent IPCC AR6 report, which shows the projected change in a percentage for DJF temperature variability on the left and JJA temperature variability on the right. And here the stippling or the hashed lines tell you when the models don't agree on the sign of the change. And what the IPCC found is that for most of the globe, the models don't agree on the sign of the change. So this is something where we thought we might be able to constrain the future projections by picking models that actually get temperature variability right in the present day. Okay. And so to do that, we're going to use this method that was come up with by my collaborator, Laura Suarez Gutierrez, to use rank histograms to try and understand if your SMILE or your large ensemble agrees with observations. And so basically the idea here is that we have one realization of the real world, so we have observations, and they are kind of influenced by internal climate variability. And so if we think about where they might sit within a large ensemble, we'd expect them to largely fall within the large ensemble spread if the model agrees with observations, maybe to fall occasionally outside. We'd expect them not to cluster too much inside the model spread or to kind of go way outside in any direction. And so basically the idea is, if you look on the right of this plot here, you get a flat rank histogram if the model and the observations agree well. And on the left here, you can see global mean surface temperature from an idealized perfect model, where you've got the ensemble spread shown in the purple lines. You've got the 25th to 75th percentile shown in the purple shading, and you've got the observations in the dots. And you can see what I kind of was trying to explain here, where the dots fall within the large ensemble bounds. Maybe once or twice they fall outside the large ensemble, but only by a little bit. They don't cluster too much in the middle. And in this case, when we're looking at how they evolve in time, we see there is some climate change signal in the global mean surface temperature response from like 1950 onwards. And you can see that that climate change response, or that warming, is seen in both the observations and the model about the same rate. And so if we can look at other kind of examples of how this works, in this case, I'm going to skip the forced response ones because I'm more interested in the variability. But here you can see what you might get if the model underestimates the variability. So in this case, you can see that the observations really cluster kind of on the edges of the model spread. They sit outside the model spread, and you get this kind of histogram that's kind of whether it's concave or convex, that kind of dips in the middle on the right. And that tells us that our model doesn't have as much variability as our observations. We can look at the opposite case where the model overestimates the variability. And here we get the hill-shaped histogram on the right. And in this case, it's really obvious to see that the observations cluster in the middle of the model spread. And you can see that the model by eye really has much more variability than the observations. Okay. And because we've currently got the kind of, we haven't detrended, you can also get effects due to whether the model and the observations agree or disagree on how much it's warming at the end of the period. And we're currently debating whether we want to detrend for our results, so we're just looking at variability, or whether we want to know whether the model agrees on how much it's warming as well. So that's kind of work in progress. And you can see in some of my other examples here that you get some weird shaped histograms when the model both overestimates the variability and, say, underestimates the forced response. So that's something that gets a little bit more complicated than the initial examples I just showed you. Okay. So when we use this method, we get something that looks like the plot shown here. So we get a map on the top left. This is for one specific model. And here you can see for each grid point, which would be that time series I just showed you, we can say whether the model gets the variability and the forced response right, or if it doesn't. And so generally in this case, if the area is white, the model and the observations agree well on both the internal variability estimate being similar to observations and that forced response, or that kind of warming at the end of the time series, being similar as well. If it's red and blue on top of each other, the observations tend to fall outside both ends of the model spread, and that means there's not enough variability in that place in the model. If it's hashed, the model tends to have more variability than the observations. And when it's one color or another, there's sort of interesting model errors going on that I won't go into detail on here. And you can see on the bottom right of this figure some examples for a scan ESM5 of how the model performs. So in panel A, you can see the Southern Ocean, where you can see clearly by eye that the model is underestimating the variability, as shown by the fact that red and blue on the map are kind of on top of each other. And this is maybe what we'd expect because this is a 1 degree climate model and it just doesn't get Southern Ocean dynamics right. It doesn't have eddies. In panel B, you can see South America. And in this case, you can see that the end of the time series, the forced response is wrong. So this model is warming over South America much more than the observations are. In panel C, you can see the North Atlantic, and this is a case where the model has too much variability, as you can see by those dots really clustering in the middle of the spread. And on the bottom right, you can see Europe, and this is where the model is good in this case. And we actually do find that most models are good over Europe. Okay. So what we wanted to do in this study is we wanted to apply this evaluation method over all of these IPCC boxes you can see on this figure. So we've got the land boxes on the left and the ocean boxes on the right. And rather than do this for the annual mean, what we wanted to do is we wanted to do this for DJF and JJA because we think that the variability might be different in the different seasons. Okay. And so we have these giant tables that tell you how well the models perform, and I'm not going to show them to you right now because they're just, you wouldn't be able to see anything on your screens. But we find some kind of interesting results. We find that some models are highest performing, so they perform well over more regions. And for DJF, that's a couple of models like CSM2, GFDL SPEAR, and one of the MPI models, but actually ACCESS-ESM does pretty well in DJF as well. In JJA, it's some of the same models, but not exactly the same models, which is interesting. There are regions where most models perform well, and those tend to be large land masses in the Northern Hemisphere, so places like North America and Europe. There are places where the models tend to perform poorly, and they are places like Southeast Asia and Australia and parts of Africa. And those regions are somewhat different between the two seasons as well. And we do also find that the models tend to do better in DJF than JJA. And there's been two reasons suggested for that. One is due to the NAO influence in different seasons. And another suggestion was that it's easier to get summer right, and there's more landmass in the Northern Hemisphere, and maybe that's why it, no, it's easier to get winter right, perhaps. Let me get back to that thought. But yeah, that it's easier to get one of the seasons right than the other. And we're still kind of looking into whether that's really true. Okay. And so that brings me to my actual science question, which wasn't the evaluation, but it was, if I pick models that perform well over each individual region in each individual season, can I constrain the future projections for temperature variability? And so here I show a bunch of regions, and I'm just mostly showing this for illustrative purposes. Here you can see different regions. The brackets tell you how many models are good in those regions. The colored bars are different warming levels, and that's the constrained ensemble. And the gray bars are the unconstrained ensemble. And here you can kind of just see by eye that when you constrain more, so when you throw out more models, your error bars tend to get less, which is kind of what you'd expect. The more models you throw out, the less of a spread there is. We do tend to see that the sign of the change in the multi-ensemble mean is pretty similar in the constrained and the unconstrained ensemble, but it's the spread around that that tends to get constrained by chucking out the models we don't believe do well. Okay, so what does this look like on a map? And we've got two versions of this map, one where we do the evaluation just as is, and one where we detrend just to get at the variability. And we think we're currently leaning towards using the detrended ensemble evaluation, but I'd be interested to hear people's thoughts on that. And so this is the one that isn't detrended, and here you can see a few interesting things. So I'll go through this in detail now. So on the left, we have the actual variability at 1 degree of warming in the ensemble. In the top, that's every smile. And in the second panel, it's only the good models. And you can see the difference in the bottom row, so bottom left. And here you can see that basically the full ensemble tends to be warmer than the constrained ensemble. So it's the top one minus the second one. The second column shows you the change in variability in DJF at 3 degrees of warming compared to 1 degree of warming. And the stippling tells you where the models agree on the sign of the change. And then the difference is in the bottom, and you can see there are some differences. And on the right, we can see the model agreement. So model agreement is shown in red and model disagreement is shown in white, and the difference is shown in the bottom. And actually, you can see our constraint doesn't really change much in terms of model agreement, which is kind of a bummer. So we can do the same thing for the detrended version, and you get kind of a similar but slightly different story. If we focus on that bottom row on the left, you can see that the full ensemble is still generally warmer than the constrained ensemble, particularly over South America, bits of Africa, and Australia. If we look at the change in variability, you can see you get larger increases in variability over South America, bits of Australia, and Africa in the constrained ensemble compared to the full ensemble. But if you look at the right, you can see again, model agreement isn't really changed. Basically, the agreement on the sign of the change isn't really improved by constraining our estimates. And that kind of brings me to JJA, which is kind of a similar story. Again, you can see those plots of the differences on the bottom. Yeah, okay. So what have I shown you? Well, I've shown you this method that shows how rank histograms can be really useful for evaluating whether the model and the observations agree on both the forced response, but also the internal variability itself. When we evaluate over the IPCC regions, we do find models that perform well and models that don't perform well. And we actually find that DJF is generally better than JJA. We find some regions, particularly most models are good, and they tend to be places like North America and Europe, big land masses that maybe it's easier to get the circulation patterns over, but also maybe where most of the models are developed and they want to do well in their own regions. Whereas regions with little islands or in the Southern Hemisphere tend to be less well evaluated. Our constraint does change things a little bit, but it doesn't really seem to improve model agreement. And so basically at this point, what we really think is that our constraint can be really useful for understanding present day variability. And so we think it is still useful to understand which models get variability right. But it doesn't really tend to help us in improving our future projections. So that tells us that the future projection sign of the change is maybe not linked to whether the models do well in the past. And that's kind of where we're at. Thanks.
Thanks very much, Nicola. That was a really nice talk. Do we have any questions? Yeah, go Rachel.
Thanks, Nicola. So presumably quite dependent on the observations and the quality of the observations. So, I mean, that Southern Ocean seemed to have some really wild variability in, what was it, the 1920s or something?
Yeah. The results are definitely dependent on observations. We are currently running this through different observational products to see if it makes a difference. The observational product doesn't necessarily make a difference, but I think there are just general observational biases that we can't account for. And we're not really sure if the models don't perform well over Africa or we just don't have observations over Africa. So I think that is definitely definitely a limitation because we can only do what we've got with the obs we have. Yeah.
Yeah, and the other thing I noticed on some of your last couple of slides, the constrained versus unconstrained. I mean, you're clearly seeing some of your region boundaries in there, which I guess makes you kind of question around the implications of using this kind of method on that kind of regional breakout.
Yeah, and that's kind of all you can really do, right? Is pick a region and then put a 1 or a 0 on. I guess you could kind of weight your models instead of just picking the good ones, which would maybe make those regional boundaries less obvious. But yeah, you can see here in Eastern Africa in the middle that there's no good models. And so there's just a big white box, which looks kind of weird, but yeah. Yeah.
On that, is there a minimum number of models you have, or is there a possibility that we're only looking at the results of one?
Yep. You could be looking at the table shows that, but yeah, there are regions where there's no good models. There's regions where there's 1 or 2, and there's regions like Europe and North America where it's all bar one model most of the time.
Okay,
so
and if
a huge range there.
And if it's just like a handful of models, are you using like multiple ensemble members or?
Yep. We're using the whole ensemble because these are all smiles, right?
Mm-hmm.
So we are using the whole ensemble.
Okay.
Yep. So the result should be fairly robust to internal climate variability, but yeah, I mean, you could totally change the sign of your change, the sign of the change by just having 2 models instead of 1 model. So it's quite dependent on where we put our threshold for what's a good model.
Yeah.
Which is another thing we're currently testing, how important it is where we decide the threshold for a good model is. Yep.
Where is that threshold currently?
At the moment, it is 66% of the IPCC region has to be defined as good. So like if you take a map and you take that IPCC region, yeah, 66% of it has to be reasonably, have reasonable rank histograms, which is also another threshold. Yeah. So.
Aidan, sorry, you had a question.
Sorry, maybe I missed it. When you were describing the smiles, is there a minimum value of the number of ensembles for each model?
In this study, we went with minimum 20 ensemble members. Yeah. Yeah. For the archive we've put together, it's anything over 10. Yep.
I guess there's a bit of a philosophical thing around, you know, a model being good for one region and not good for another region, and good in one season and not in another season. And is it then just good for the wrong reasons? You know, maybe there's a kind of, if a model doesn't get a certain number of regions good, maybe it shouldn't be considered at all. Don't know. Maybe you'd lose all models at that point.
Right? A little bit. I mean, part of the reason we also wanted to do this is to say, well, if you don't get your variability in a region right, how can you look at extreme events, for example? Because you know that they're not going to be right because your internal, you know, your temperature variability is totally wrong. And so maybe if you're just interested in the impacts of specific numbers in your region and not the large scale dynamics behind it, then maybe it doesn't matter so much. If you're interested in generally which models perform well everywhere, that's kind of why we've got this list of models and how many regions they perform well in, then maybe you want to pick models that are generally good overall. I guess maybe if you're interested in atmospheric processes that define rainfall in, I don't know, the Northern Hemisphere, then you're happy if the Northern Hemisphere weather systems are right, but you don't really care if the Southern Ocean is bad. So I guess philosophically, maybe it depends on your science question.
Yes, the all models are wrong, but some are useful.
Yeah, that's kind of where I would go with this. But I think if you don't know which ones are wrong and where and how, then that makes them less useful, right?
Aidan, back to you again.
I think you probably answered that, but have you seen Gab talking about selecting models from ensembles and basically being quite well. Anyway, I can never remember the details. I always remember thinking, "Wow, that's really smart." But I think you probably answered it by saying that you need models that actually perform well for certain tasks, I guess.
Yeah, I think so. And I think kind of the premise of this as well is that with the smiles, you can actually evaluate variability. With one run of a model, maybe the mean state's not so hard to evaluate, but variability itself is not that easy to evaluate with typical first ensemble member CMIP type data. So this is kind of a nice way to say, well, actually, a lot of people are starting to use these smiles to look at extreme events because that's what they're useful for, because there's so many realizations. But you kind of want to know if they can get variability right before you then go and use them. So
Siobhan?
Yeah, I noticed you've got some CMIP5 models in there as well. So have you been using something like SSP585 or
yeah, so that's why that plot has warming levels on it, so 3 degrees compared to 1 degree, because the SMILE archive is CMIP5 models with RCP 8.5 and CMIP6 models with either SSP 585 or 370.
Yeah. Okay.
Because we took what we could. It's a ensemble of opportunity, not a MIP. So that's
good. Yeah, I mean, I saw the Sarah Mark V6 was still there and the CSM one was there, and I couldn't pick all the other models where they all came from. But yeah, it was good. It was good to see, at least to see that Sarah Mark V6 was still being used.
Yeah, it's still being used. Unfortunately, it does evaluate quite poorly for a lot of metrics, but
yeah, I'm not sure it would be doing that well, but at least it's being picked up by some people. Some people like it in some places, which is interesting.
Yeah, it's I think it's got 30 members, and that's RCP 8.5.
Okay, yeah, it had 20 at one point, but they may have done more. Yeah.
Okay.
But yeah, I could see on some of the plots it was.
Sorry, Siobhan. Harun?
Yeah, Nicola, I was a bit distracted at the beginning of your talk. You might have talked about it. So you said that you have a minimum of 20 ensemble members, but you have also models with more ensemble members. So you didn't take more. So there were variable numbers of ensemble members. So is the model performance somehow related to that, say, the more ensemble members a model has? No. Yeah?
No, we checked that.
Okay.
Yeah, we definitely, because 2 of the models that do perform really well are 2 of the larger ensembles, but we checked it. We redid the calculations with less members and we get the same answer. So
okay.
yeah.